Hello everyone, and welcome to Lab Manager's Tech Trends webinar series. My name is Trevor Henderson, Technology Editor for Lab Manager, and I'll be moderating today's discussion, which will focus on new developments in material testing. We like our webinars to be very interactive, so we encourage you to send us your questions at any point during the presentation, and the panelists will address these during the question and answer session following the webinar. To ask a question, simply type your query into the Q&A box located at the bottom left-hand side of your screen, and we'll try to address as many questions as possible during the Q&A session. If we happen to run out of time, I will forward any unanswered questions to the panelists, and they can respond to you via email. Additional resources may be accessed via the file folder icon located at the bottom of your screen. You may also move or resize any of the windows simply by grabbing them at the top or stretching them at the bottom right corner. At this time, you may need to move or minimize some of the open windows to see the live view. This webinar recording will be available early next week on Lab Manager's website, and at the end of this webinar, we'll share that link with you, as well as the contact information for our panelists. With that, let me introduce our first speaker, who joins us today from Agilent Technologies. Steve Wilbur is the Software and Peripherals Product Manager for ICP-MS products within Agilent Technologies' Life Sciences and Chemical Analysis Solutions Group. Steve joined Agilent's ICP-MS team as an applications chemist with the introduction of the 4500 ICP-MS in 1995. Since then, Steve has been instrumental in the advancement of environmental ICP-MS at Agilent. His accomplishments include development of the original ICP-MS EnviroQuant software for the Integrated Sample Introduction System, ISIS, as well as contributions to the Intelligent Sequencing Software and GC interface. In his current role as product manager, Steve continues to guide the development of new ICP-MS peripheral hardware software at Agilent, including the newly introduced Nanoparticle application module. Thank you for joining us today, Steve.
Thanks, Trevor. Thank you very much. And I'll go ahead and get started. The title of my talk today is Characterization of Nanoparticles by a Single Particle ICP-MS. So first of all, let's talk about the definition of nanoparticles. There's been interest in nanoparticles for quite a number of years now, and as a result, in 2008, the International Organization for Standardization, or ISO, defined a nanoparticle as a discrete nanoobject where all three Cartesian dimensions are less than 100 nanometers. In 2011, the Commission of the European Union endorsed a more detailed but wider-ranging definition that encompasses particles of different relative dimensions. And that definition states that a nanoparticle is a natural, incidental, or manufactured material containing particles in an unbound state or as an aggregate or an agglomerate where for 50% or more of the particles in the number size distribution, one or more dimensions is in the size range between 1 and 100 nanometers. So that encompasses things like nanofibers and particles that aren't necessarily spherical in shape. So to give you an idea of the relative size of nanoparticles compared to some particles or things that you may be familiar with, I've borrowed this handy plot and I've highlighted the nano range in yellow on the left. That's the region between 1 and 100 nanometers. And you can see that that includes things like the HIV virus, some common proteins, and other small particles you may or may not be familiar with. Now note that the y-axis is a log scale here. And if you look to the far right at the top, you can see E. coli bacterial cells, white blood cells, red blood cells, and human hairs. And so you can see from this, this graphic that, in fact, nanoparticles are orders of magnitude smaller than biological cells or human hair. The images at the right are electron photomicrographs of nanoparticles of different sizes and shapes. So you can see that the European definition is actually necessary to quantify these particles at the bottom that are long, narrow shapes. So why are they so important? Well, it turns out that nanoparticles have very novel physical and chemical characteristics that are based on a lot more than just their elemental composition. It turns out that their very large surface area to volume ratio imparts a large role of intermolecular or surface forces, and that increases the solubility significantly. It increases the vapor pressure, which results in lower melting temperatures than you would have for normal sized particles. Nanoparticles have very high surface energy, and they also have very high absorption of EM radiation, so they're used in things like photovoltaic cells and sunscreen, for example. The graphic at the bottom is interesting. It shows a 1 centimeter cube on the left and calculates the surface area of that cube, which is obviously 6 square centimeters. If we take that same volume, that same 1 centimeter cube, though, and divide that into 1 millimeter, smaller 1 millimeter cubes, then the total surface area increases by an order of magnitude to 60 square centimeters. Along that line, if we take that same 1 square centimeter cube and divide it into cubes that are 1 nanometer on a side, now the total surface area has increased to 60 million square centimeters. So you can see the effective surface area is enormous when you go to really, really small particles. So nanoparticles come in all kinds and shapes and sizes. There are natural nanoparticles, and more importantly, at least for the content of this topic, there are engineered nanoparticles. And engineered nanoparticles are used in almost everything you can think of in some way or another. They're used in consumer goods, pharmaceuticals and medical research, semiconductor manufacturing, foods and food packaging, ceramics, semiconductors, electronics, agriculture, defense. Just about anything that's manufactured now has nanoparticles somewhere in the supply or manufacturing chain. So there have been a number of methods over the years for nanoparticle characterization, ranging from imaging methods like transmission or scanning electron microscopy or atomic force microscopy. There are spectroscopic or optical methods, including UV vis and dynamic light scattering. There are hyphenated techniques where a chromatographic or other online separation system is coupled with a detector, typically ICP-MS. Examples of that might include field flow fractionation ICP-MS, or capillary electrophoresis ICP-MS, or HPLC ICP-MS. I'm showing a couple of examples in the photographs here of field flow fractionation systems connected to an Agilent 8800 triple quad ICP-MS in the center and an Agilent 7900 single quad ICP-MS below. And then finally, there's single particle ICP-MS, which is the topic of today's discussion. So single particle ICP-MS has gained a lot of notoriety in the last several years, mostly because it has a number of really important benefits and only a few limitations. The main benefits are that it's a very simple technique, and it's also a very fast analytical process. Minimum sample preparation is required. If the particles are in suspension in a liquid, then they can probably be analyzed directly, maybe following some simple filtration to remove larger particles and possibly dilution. The technique provides the mean particle size and the size distribution. It provides elemental information. It provides the particle number concentration and mass concentration. And it can also provide the dissolved ionic concentration of the elements that are in solution. It does have some limitations, though. An important one is that the minimum detectable particle size is determined by the analyte sensitivity to background for the instrument. And it's not possible to gain sensitivity by pre-concentrating the samples as you would with other techniques. Internal standardization can be challenging because typically nanoparticles are suspended in neutral pH buffers for analysis so that they don't dissolve, and internal standards are not always stable in those neutral buffers. There's a relatively narrow optimum range of particle number concentrations compared to some of the other techniques, and it's typically limited to 1 or 2 elements. So let's just do a real quick background for those of you that are new to the technique. Single particle ICP-MS is actually quite simple. I'm showing on the left a sample containing a number of individual nanoparticles in suspension. Those nanoparticles in that solution would be pumped into a nebulizer and a spray chamber. And if the solution is sufficiently dilute, the aerosol droplets that are created by the nebulizer and eventually make it into the plasma should have not more than 1 nanoparticle per droplet. And ideally, most droplets would have no particles. So in that case, as each aerosol droplet enters the plasma and it's atomized and ionized, it'll generate a plume of ions from the nanoparticle that was in the droplet, and that plume of ions is representative of the mass of that particle. If those ions are then analyzed by ICP-MS in time-resolved analysis mode, each particle will generate a signal over a specific time that looks a lot like a chromatographic signal. And the total area under that curve, or that total signal, would be representative of the mass of that particle or particles that were in that particular droplet. So it's quite simple, but there are some issues to consider. And one of those is the concept of dwell time or integration time or scan time. There's different ways to describe that. But when the ICP-MS is looking at a particular signal, it acquires that data and integrates it over a certain amount of time called the dwell time. And so on the left in the gray box, I'm showing a single nanoparticle event, the time it takes for the ions from a nanoparticle to elute from the plasma. Generally, that's around 0.5 to 1 milliseconds in duration, and that's relatively constant. And so if we have this nanoparticle eluting from the plasma over around half a millisecond, and we're scanning using what are, at least in the nanoparticle world, considered to be long dwell times, around 3 to 5 milliseconds, several things can happen. And so I'm showing on the right center 5 yellow boxes, each of those representing 1 dwell period or 1 scan. And I'm showing 4 nanoparticles eluting randomly from the plasma. So the first thing that can happen is the nanoparticle can come out somewhere in the middle of the scan, and it would be measured and integrated and create a mass spectrum that I'm showing below that, the intensity of which is proportional to the mass of that particle. The other possibility, though, with long dwell times is that more than 1 particle could elute during a single scan. And in that case, the entire intensity from the multiple particles, in this case I'm showing 2, would be integrated and generate a mass spectrum that I'm showing below that would in fact be proportional to double the intensity of each of those particles. It's also possible for a particle to randomly elute between 2 scans, or partially in one and partially in the next. And if there's some settling time between scans where no information is acquired, then some of that intensity would be lost. And so you can see, looking at the mass spectrum below, there's a very small peak representative of scan 3 and a small peak representative of scan 4, which represent the tails of that peak. And a large part of that peak was lost in the settling time between those 2 scans. The final thing that can happen, which is actually the most common, is that no peak elutes at all during the scan, which is the 5th block on the right. But in that case, you'll see I've still shown a small signal in the mass spectrum, and that signal is really the background, the non-nanoparticle contribution of the sample to that particular mass. And that could be the basic instrument background, it could be interferences from polyatomic ions, and it could be dissolved ionic concentration. So background is important to consider as well. So it might seem that if we could shorten the dwell times to very short dwell times, we could solve that problem of multiple peaks eluting during a single scan. So again, in the gray box, I'm showing the same single nanoparticle event around half a millisecond wide, and I'm showing 5 scans in this case that are much less than 1 millisecond. And you can see what happens then is if the nanoparticle event is longer than the scan, then the entire nanoparticle signal will never be contained within a single scan. And you can see in this case the first two scans are actually splitting this peak, and the intensity in the mass spectrum in both cases is not proportional to the total peak. It's proportional to the part of the peak that fell within that dwell period. You can also see that no matter how short you make the integration time, it's still possible for two nanoparticles to elute close enough together or co-elute to cause the signal to be non-representative in a high fashion. So, in fact, very short dwell times don't completely solve the problem, and correct dilution is still really important to avoid the situation where multiple particles elute during a single dwell time. So how do we solve this if just using short dwell times doesn't resolve the problem completely? And the way we do that is by using very short dwell times, what we call microsecond scanning with no settling time, so that there's no loss of information between scans. And in this case, we're using very, very short dwell times, much less than 1 millisecond. And then we're using what we call peak integration mode, which means we're summing or integrating the signal over multiple scans. This is very much like a chromatographic peak would be integrated. So again, the same single nanoparticle event is shown in gray on the left. As it elutes from the plasma, we can scan multiple times across that peak, and each of those scans generates an intensity in the mass spectrum that I'm showing below. That's proportional to the mass of the fraction of the nanoparticle event that eluted during that dwell time. And we'll get multiple scans across the peak that can do two things. They can define the shape of the peak, which helps us identify whether or not there are two very close or nearly co-eluting peaks. And then if we can sum the intensity of each of those scans across that peak, we can generate a single scan, the intensity of which is proportional to the mass of the peak. So that's the way we solve the problem of very short dwell times and eliminating multiple peaks within a single scan. So if we take a look at sort of the workflow on that, this is some data that was acquired on an Agilent 7900 using 100 microsecond dwell time and no settling time. And if you do the math, you'll see that 100 microseconds gives you 10,000 data points per second, or 600,000 data points per minute. This is a 1-minute run, so on the lower left, that raw TRA data plot shows you the 600,000 data points that were acquired over the course of this 1-minute run. In the center, we've zoomed into about a half-second wide section of that raw TRA data, and you can see that, in fact, the individual nanoparticle peaks are well separated. And then on the upper right, I've zoomed in to even a closer look at the two peaks that are circled, that are very close together. And you can see that the peak shapes are well defined, and those two nanoparticle peaks are baseline separated, even though there's less than 2 milliseconds difference between them. So the workflow then is pretty straightforward. We acquire the data in fast TRA mode using very short dwell times, very short integration times, and no settling time. You can see that on the upper left. Then we sort that data or convert it into a response versus frequency plot. So we sort all the data around particular responses, and you can see that if there are nanoparticles over a size distribution range, we'll see those clustered by response. So now we've got the particles sorted by response, and we need to convert that to mass and size distribution. And to do that, we have to add a fair bit of information. We have to add an analyte response factor to convert the response into the mass of the particle. We have to add nebulization efficiency information. We have to add the analyte density and the analyte mass fraction in the sample particle, and those allow us to convert the mass of the particle to a size. And then finally, we need to tabulate and report that information in a form that's easy to understand. So that used to be a relatively complex process. It used to be done either by hand or using Microsoft Excel, and in any case, it would take minutes or hours per sample to do the calculation. So we've simplified that by using the nanoparticle application module in the Agilent Method Wizard, and we've reduced it to just 3 steps. And the first step is to select the analysis mode. I know this is a little bit hard to read, but in the center you can see that we've added the nanoparticle analysis mode, and you can just click the button that says single particle analysis. And then if you click the next button, after that you will go to step 2, where you just point to the elements on the periodic table that you want to analyze, and then you click next, and you select the reference material that you're going to use from among the standard NIST reference materials, for example. Once that's done, the entire process is completely automated. You put the samples in the autosampler and press go, and the results are automatically generated, and no further user action is really required. And the results will look something like this. This is a result table of 10 replicate analyses of or actually 5 each of the NIST reference 30 nanometer gold and 60 nanometer gold, an ionic calibration, and then a spike of the NIST 60 nanometer gold into tap water. And so the results in this table were created fully automatically after using the Method Wizard to set this up. We ran this particular set of data to take a look at the precision and accuracy of this determination using the 2 NIST reference materials. And so again, we calibrated on an ionic solution, and then we ran 5 replicates each of the NIST 8013 60 nanometer and 5 of the NIST 8012 30 nanometer gold. The 60 nanometer concentration was 100 nanograms per liter prepared, and the 30 was 10 nanograms per liter. If you look at the red in the middle of the upper table, you can see that the calculated observed concentration came out to be 103 nanograms compared to the 100 that was prepared. So the recovery is quite good. And the observed concentration for the NIST 8012 came out to be 10.5 compared to the 10 that was prepared. So again, the accuracy is very good. The observed calculated particle sizes were 55 and 28 nanometers respectively. The reference sizes by transmission electron microscopy were 56 and 27.6. So the particle size accuracy is also very, very good. We also calculated the precision as relative standard deviation for the 5 replicates of each. And we calculated that for the number of particles for both sample sizes, the concentration of particles per liter, the concentration in nanograms per liter, and in all cases the relative precision or the relative standard deviation was around 3.5%, so that's quite good. We also calculated the precision of the ionic concentration measurement, which came out to be between 2 and 4.7%, so again quite good. And the background equivalent diameter precision, which is the particle size detection limit. Again, the precision or RSD was around 1% roughly. And what was really impressive to us was the precision of the particle size measurement. You can see on the 60 nanometer particle, the relative standard deviation over the 5 replicates was 0.1%. And even for the relatively small 30 nanometer particle, the precision was 0.4%. So that's all I have to say today, and I thank you very much for paying attention, and I'll hand it back to Trevor.
Well, thank you very much, Steve. And thank you all for sending in your questions. I encourage you to continue to do this throughout the presentation. If you joined us late, you can ask questions simply by typing your query into the question box, which is located at the bottom of your screen. Our next speaker is Kate Comstock, who joins us from Thermo Fisher Scientific. Kate is a marketing specialist in pharma applied product marketing at Thermo Fisher Scientific in their chromatographic and mass spectrometry division in San Jose, California. Kate has a Bachelor of Science in Chemistry from Hebei Normal University in China and a Master's in Science and Chemistry from San Jose State University. Kate worked at the core mass spectrometry lab at Roche Pharmaceutical for 20 years, supporting drug R&D and production using LC-MS for impurity ID and structure elucidation. Kate joined Thermo in 2010 as a marketing specialist to support new product development and applications using high-resolution mass spectrometry. Welcome, Kate.
Thank you, Trevor. Hi, everybody. Thanks for Steve's great presentation on nanoparticles. Now I'm going to talk about a more general and broad subject, which is the extractable leachable analysis, and we'll touch upon the instruments, software, and the database. Here is a brief outline. And what is the extractable leachable? The industry need to do the ENL analysis, and the current regulation, and also for the analysis itself, what kind of instrumentation, what kind of software and database spectral library needed. Especially, I'm going to talk about the high-resolution mass spec for extractable leachable analysis through a case study. Here is a brief definitions. Extractables are the compounds that migrate from the surface under more aggressive conditions of exposure, for instance, different solvents, time, and temperatures. Well, leachables are the compounds that are migrated from the contact surface to drug formulation or human body if it's medical devices under under normal conditions of exposure. In general, the extractable is more about the material safety. Extractables most are the additives, impurities, polymer components, and some of the degradants. And well, leachables are partially are the non-extractables and also the interactive product of the drug formulation and the non-extractables, and also some of the extractables modified by the process conditions. Some leachables are subset of extractable, but not always the case. So who does extractable leachable analysis? There are many industries. First of all, Pharma and Biopharma, from the starting R&D to production until the final product field. So both upstream and downstream. Especially right now, the bioproduction start using a single-use system, so that make the extractable leachable analysis more important. Also, medical devices. Medical devices encompass many different things. So important things, they all make contact with the human body, no matter it's implants or diagnostic devices or prosthetic. High purity polymer and rubber suppliers, because they are raw material supplier for the medical devices and some surgical instruments. Another big area is food, beverage container packaging. All the bottles, bag, plastic wrap, the labeling adhesive, printing inks we deal with every day need to do extractable leachable analysis. So why the extractable leachable analysis are important? Because they are chemical impurities. They could contaminate the medicine, food, and drink, and cause adverse effects to consumers, especially the biological drug. Mostly administered through the injection or infusion. So they get into the human circulation system in just a second. So that's why it's so important to make sure those container packaging we are using for the medicine are safe. And also ENL analysis are highly regulated. They are required for market approval for any new product or devices. And the ENL analysis are very challenging and complex. They need multiple instruments, techniques, and also need expertise to do the data processing and analysis. Therefore, we'll need adequate software and database. And the last but not least, ENL analyses are tedious and time-consuming. You must start at the early stage to be ready for new product launch. Over the years, there are increased regulations, and more and more stringent regulations come from all over the world, especially in North America and European countries. Extractable and leachable analysis include sample preparation. There are multiple techniques and multiple solvents required. And then you need to do separation, identification, and quantitation. Because there are varieties of compounds involved. Therefore, GC-MS, LC-MS, ICP-MS, and others instruments like ion exchanging chromatography, UV, FDIR, CAD, which is charged aerosol detector, are required. And a lot of data being generated. So the data analysis actually is a big part of the whole process. At the Thermo, we have all the systems and the software database for ENL analysis from the sample prep to GC-MS, ICP-MS, and the high resolution mass spec, also the software database suite. I would like just particularly talk about the high resolution mass spec for ENL analysis. As I just mentioned, ENL analysis essentially is a known and unknown impurity analysis. So for impurity analysis, require component ID and the structure elucidation. So the high resolution accurate mass acquired from the high resolution mass spec provide accurate information for component identification and the elemental composition assignment and structure characterization based on the high resolution accurate mass MS data, and also because the sample tend to be complex, especially the leachable samples. There are a lot of matrices and instrumental background. So the high-resolution quantitation can effectively eliminate matrix and the background interference. Because by the time you need to do quantitation, most likely those particular compounds, the compounds have some toxicology concerns. So to be able to do, lower your LOD is very important. Here, just to show you a very simple example, the benefit of a high resolution. And we have two pesticide mixtures. as we can see, at the 17.5 resolution, and we are not able to separate these two components. Therefore, and also you couldn't do accurate elemental assignment because the number you got is kind of mixture, right? Average of these two compounds. When we use the 35,000 resolution, these two peaks are partially separated. When we increase to 70,000 resolution, they are baseline separated. And when we use 140,000, they are complete baseline separated. So this is just a very good example. How can you do accurate, confident component identification use a high resolution mass spec? And then here show you by using a polarity switching, still maintain high mass accuracy, help you identify the degradation product. Here we show a degradation product for one of the common antioxidant. Also, as we all know, the fine isotope structure is very important when you do unknown impurity analysis. So this is actually the oil additive mixture run in the Q-Exactive, use 70,000 resolution. And when we zoom in a small peak, we can separate. And then if we take a close look, the A2 isotope, we see a sulfur split. So based on the information provided here, we can confident and come up the elemental composition. And also here, in the bottom right corner, we list the name and the mass accuracy and the elemental composition. By the way, this is acquired in the negative I mode. Also, the quantitation is important. Like I point out, when you do the quantitation, most likely are the compounds have a toxicology concern. Here we just use a common antioxidant, Erknox 1035, prepared in the common food simulant, and then use high resolution quant. We were able to get a very good, linearity. And normally, this is the regulation. I think is in the ppb level, but in this particular case, we were able to get 50 ppt, 0.05 ppb. And this slide shows the accuracy and the precision, and so it's pretty good. Also, the instrument method setup is very simple. Basically, drag and drop, and just put whatever the mass range conditions you need it. As I point out, the data analysis actually is very important. It's a big part of the whole process. We have this small molecule quant core software suite, and they are all very good combined by using them, and can provide accurate information for the data for the result, because the regulatory agents want to have not just the quantitation and qualification, and also you tend to need to do a lot different batch lot, and by using the software here, you can easily find the difference, compare either during the production process or different lot batch in your particular area. Those software, I'll just quickly go through some of the features. Those for this particular software, we call Compound Discoverer. You can simply do the set up the processing workflow and result review, and then do structure elucidation and generate the report. If you want to come back, tweak the analysis a little more, you can just simply change the parameter a little bit in the processing workflow and then run it again. So it's a very automatic. And we all have the unknown problem, right? So for actually unknown impurity ID is the toughest task for anybody. We have a software called Mass Frontier. I think it's a great tool for structure elucidation. The best part is this software has a built-in fragmentation mechanism library. So if you have any unknown impurities, as long as you have your MS mass spectra, you can use the knowledge and the information proposed structure, and then use the Mass Frontier do the fragment prediction. And the best part is all those prediction, those mechanisms in the software is actually collected from the published articles, so they are some scientifically sound. So if those if their prediction are right, so the theoretically generated fragments will be automatically annotated, and so and also color coded. So here the red line means there is a theoretical backup, right? This particular either mechanism or this structure present in the fragmentation library. And also we have this mzCloud high resolution spectral database. This is a free, right? Anybody can use it. The good thing for this is provide a high resolution accuracy and the different collision energy for the compound. So the search actually is very easy. All you need to do is copy your MS mass spectra, either MS2 or third, whatever, based on your experiment, and then just click go, and then if the compound is present in this database, and then mzCloud will show you the matching score on the upper left corner, and then show you the spectral compare, and also give you the structure. So it's very handy. Now here I just use one experiment quickly demonstrate this workflow. So this is simple. This is the IV bag. We everybody knows, and then because the compounds we deal with, so we use the GCMS, LCMS, and ICP-MS to capture the whole range of the compound. And then the workflow actually is very easy. Right? So you just use the Q Executive, and all the data acquired simply put in the safe software, and then you can identify it either by your own library or through the chemical ChemSpider. And then for the if you have doubt, just simply use the Mass Frontier to predict the structure, and then do the structure prediction through the Mass Frontier fragment mechanism function. The instrument method is very easy, right? It's both basically you want is get as much information as possible for the component ID and then come up with the structure. So this is a partial list for the analysis result. So the middle yellow column indicate every component identified has a very good method accuracy. So that really increase the confidence for the structure you proposed. This is just all those technique support you could use. There are a lot of information online, and also if you can get all the hardware, both hardware software details from the Thermo's website. So without that, I would like to thank everybody.
Great, thank you, Kate. I believe we'll go directly into our question and answer session. We do have a number of questions that have come in from the audience. And Steve, if you're back, I think I'll direct the first question towards you. Now,
I'm here,
Steve,
thanks.
Good. Is it possible to measure single nanoparticles of elements which are subject to interferences by using ICP triple quad?
Yeah, actually, that's a good question, and it is definitely possible. And in fact, we've got a number of users using the 8800 ICP triple quad to measure nanoparticles composed of things like silicon dioxide or titanium dioxide that are very difficult to do by single quad ICP-MS.
Great, thank you. Now, Kate, why is high-resolution mass needed for extractable and leachable analysis? This person says, my lab's been using LCUV for E&L analysis for quite some time now.
Yeah, that's actually very common in the industry. Yes, a lot of people are just using the UV, but as I point out, in a lot of time you are dealing with unknowns. So the first thing you need to do is measure have accurate information for the elemental composition. So as I showed in one of the slides, if you don't have accurate mass, sometimes can lead you to the wrong way. That's why you want to have accurate mass, have the right elemental composition, and then you can do the structure elucidation. So I think the UV only technique is not going to be enough.
Thank you. Now, Steve, in regards to single particle ICP-MS, what is the observed saturation concentration for the technique, or is it a function of the mean particle size?
That's a good question. I'm not exactly sure what saturation concentration means if they're talking about dynamic range in particles per unit volume. It actually depends not so much on the particle size, but on the things like plasma conditions and carrier gas flow. So it's a little hard to give an exact answer to that question. I'm sorry.
Well, that's fine. Maybe we can follow up a little more offline with that question. While I do have you, what is the minimum particle size that can be measured by using single particle ICP-MS?
That's actually a good question, too, and that depends a little bit on the response factor for the element. But for elements with good elemental response like silver or gold, if the background is clean enough, it's quite easy to get down to around 10 nanometers or so.
Great, thank you. Now, Kate, is it possible to get demo copies of the data analysis software you spoke about?
Yes. You can log on the website I listed in the last slides and get the 60 demo version.
Great, thank you. And Steve, now does the nanoparticle method wizard that you mentioned work with all the Agilent ICP-MS models?
It does. It works with all the currently supported models. It requires an upgrade to the most recent version of MassHunter software, which also supports all the current models.
Okay, thank you. And Kate, is there a high-resolution GC-MS spectral library that's available?
Currently, I don't think so from Thermo side, but we are working on it, so that will be part of the mzCloud high-resolution database. Yeah, that's a good question too.
Okay, thank you. Well, we've come to the end of our questions, so I thank you for your presentations today, and this brings us to the end of today's webinar. Just a reminder that today's webinar video will be available at the link you see on the screen now. And on behalf of Lab Manager, I'd like to thank both of our panelists for their hard work that they put into their presentations. And I'd like to thank our sponsors, Agilent Technologies and Thermo Fisher Scientific, for supporting our Tech Trends webinar series. As well, I'd like to thank all of you for taking time out of your busy schedules to join us today. Please mark your calendar for our next Tech Trends webinar, which will focus on sample prep for mass spec. This webinar will be taking place Thursday, July 23rd from noon until 1:30 p.m. Eastern Daylight Time. For more information on this and other Lab Manager webinars, please visit our website at www.labmanager.com. We hope you can join us again next time. Thank you and have a great day.